Okay, good afternoon, everyone. Let's continue with transformers. Actually, before we dive into the next part of the transformer, I realized that there is an issue with Canvas and Piazza and everything right now. I have no idea how long it's going to last. I know some of you asked questions on Piazza, which now becomes really hard to answer. So I and TAs are going to stick around a little bit after the lecture. So if we didn't answer to you over Piazza, please ask us here. Send us an email, CC both of the TAs in case Piazza isn't working and you need assistance. Now, it could happen also that the Gradescope isn't accessible. I don't know whether that's the case right now.
Looks like Gradescope is still running.
Gradescope is still running. I will send them. I think I did finally add links to Piazza and Gradescope and everything on the website. So can I, sorry, Ashley, is it? Can you maybe open the website and see whether you can open Gradescope from the website if you don't want to see laptop open? If that works, then you all have access to Piazza, to Gradescope, and everything should work fine for the assignment. But yeah, if you can't reach us over Piazza, please feel free to send an email and CC Nate Reifer, and also add a little CS 63405340 in the subject such that we can for your emails. Did you check by any chance?
So Gradescope does work, and right now Google Piazza also works.
Okay, and you can access Gradescope from the web page. Yeah, perfect. Okay, so our course web page has links to Gradescope and Piazza, so you don't need to go over Canvas because honestly, that's how I usually put these links. So I think everything should be then fine for our course, but let me know if there are any other issues that you are noticing. Okay, now going to the topic where we left things off. Our next goals, since we have came here after the fall break, were to introduce some changes such that we can have a better starting point to build a lot of solutions for a lot of applications, from question answering to summarization to translation. And we started with better tokenization. You all are working on BP tokenizer right now, so I'm pretty sure by now we all know what that means. But then we started to introduce different, better neural architecture, namely transformers. And last time we have introduced some changes to handle longer text better at least relative to the RNN or the LSTM, to model word order, and to also produce contextualized rather than static representations of tokens in the let's see whether you remember which architectural change had addressed this. So what helped us to model longer text better, namely when we come to the later parts of the text, that we still somewhat have a chance to remember what we have seen indeed. So which part of the architecture helped us with that? Yeah. Self-attention, that's right. So with self-attention, we have introduced a mechanism that allows every token, regardless of its position, to attend to every other token. So if I'm producing a representation at the end of my text, I still have a chance through self-attention to attend to the beginning. So I can, for example, if I had a problem of coreference resolution where I have some entity and different mentions of that entity, if I had to refer to that entity with the pronoun at the later stages of the text, I still have a chance to understand which entity that pronoun is referring to. How about modeling word order? Which architectural change had allowed us to do that? Yes, please. Positional embeddings. I would say positional encoding. I know I was imprecise with that. We are going to start using the word encoding rather than embedding, because sometimes now, these days, we are doing it through rotation and we are not actually introducing embeddings. But yeah, now we have this extra element in the architecture that allows us to know in which condition is the text What did you not cover there?
Some metal part though, right?
So yeah, we now know which word appeared in which position, and I should actually say token rather than word. And this allows us to now understand the difference with this architecture between dog eats chicken and chicken eats dog. Okay, how about contextual representations? How did we do that? Which mechanism helped us to produce contextualized representations? Do you remember what contextualized representations are? Can you first repeat what contextualized representations are before you answer my first question?
Contextual representations are an representation of a word which embeds meanings or symbolic relations with other words around it. So, and we use encoders to calculate meanings.
Gotcha. So yes, contextualized representations are representation of each token where we have integrated information about other tokens in the input. And in this way, we have a chance to see disambiguate tokens that have multiple senses. Now, instead we managed to do this with encoder, and that's not wrong, but a little bit broad. There was something specific within encoders that allowed us. That attention, a little bit shy, but that's a correct answer, right? So now every token attends to other tokens. We get the weights of how important each token is to this current token we are producing a representation for, and then we use this information to enrich our representation to the product of the attention matrix with the effect matrix, right? So those were the mechanisms we were kind of introducing, and as you can see, I kind of crossed out most of the things we wanted to achieve. However, we haven't really wrapped the entirety of transformers, so we are going to go over the remaining bits and pieces to have the understanding of the full architecture. Yes,
So how is the attention used for the embeddings different from the attention used between the layers or used in each block?
Sorry, can you repeat that?
Okay, so we use the self-attention to get the contextualized embeddings.
Yeah.
Which you said is the attention matrix times the values.
Yeah.
Yes, times the values. And so that's different from the multi-headed attention used for each block.
I wouldn't think about them as different things. I wouldn't think about multi-headed attention as just a attentional steroids.
Yes, they're both multi-headed, right?
So not really. Attention matrix times multiplication of attention matrix with the value matrix. This corresponds to a single attention head. Then when we take outputs, let's call these seeds as we did last time, and when we concatenate them, we get this really large vector for each token, which we then down projected to the final output, which is the output of the multi-headed self-attention.
And that's used for the embedding and between layers.
I think you're doing something about layers which doesn't have extra meaning. So basically, we have a token for embedding for some token I, right? And we, with the single attention mechanism, we are going to produce Z J equals AJ times BJ. So that's the output of a single attention head, right?
Okay.
And we are going to do this, many of these in parallel, right? So we're going to have ZJ plus 1, ZJ plus 2, and so on.
For each position in the input.
For each position in the input, we are going to have multiple attention heads.
Yes, yes.
Okay,
And so that's J is the number of the attention head.
yeah, okay, yeah. So J goes from, let's say, 1 to number of heads, and number of heads can be in simpler models, something like 8.
Okay.
Okay, so we have all of that, and then from all of these, for a single token TI, we are going to produce Z, which is going to be concatenation of all these vectors, right? Z1, 2, the number of hits. So this is going to then be the representation, one vector representing the token Ti, and then we are going to down project it to a vector of a smaller size. And that's going to be output of a multi-headed self-attention. This is an output of a single attention head. This is an output here, let's call it Z tilde, output of the multi-headed self-attention. But this is all happening, I think you were saying something about the cross layers that I didn't quite get it.
For each transformer block, it contains the self-attention.
Yeah.
Contains a feed-forward network and a self-attention.
Yeah,
And so to use the same mechanism for each block as well as to create the embeddings. Maybe I'm. missing
yeah.
something.
I think maybe if I can kind of infer what might be confusing you is how do we repeat this? So the way you repeat this is now, this is your current representation of token Ti. In the next encoder block, that's the input to the encoder block. So you repeat everything, but your input, instead of being what we have called X before, now you have this Z tilde. And now you are doing all of this starting from this output of the previous encoder block. So as in standard deep learning.
Okay, so you're saying there's no difference.
I can't quite pinpoint what confuses you, so maybe let's take this offline just because we need to move on.
I think I'm understanding what he's trying to ask.
Uh-huh.
Self-attention as an architecture concept, it's responsible for both handling those long texts and handling the contextualized embeddings. Is that correct?
Mhm, yeah.
Okay, so it's that same sort of, architecture as a whole that handles two different concepts.
Sure, it does, but I don't see how these two questions are connected. This is I think.
It's whether there's like one sort of self-attention mechanism that is responsible for handling long text versus a different quote unquote self-attention mechanism responsible for contextual embeddings. Are they different or is it still the same self-attention?
No, it's the same self-attention. Let's not overthink this. I introduced a single mechanism and we are applying it. Why would
That's
there
what I
be
was
two
thinking.
different attention mechanisms?
Yeah.
We have learned just one, so why would there be more than a single one? We are going to introduce something called cross. We're going to go from decoder to encoder, but that's going to be another type of attention. But right now we know only this type of attention, and it is helping us with two things at the same time. You are right, but I think there was some confusion with how encoder blocks are stacked together. So yeah, let's move forward. Let's chat more after.
You're using the term transformer.
Yeah.
Encoder blocks, are you referring to transformer blocks?
Yes.
When you say any, okay, so if there's any transform. When you say encoder block, are there multiple blocks stacked together before the main transformer blocks?
Okay, let's take a step back. Let's forget about this terminology. We are learning about transformer architecture, which we have seen a huge visualization. Here it is again. All of this is a transformer architecture, right? There is just one, it's a one entity transformer architecture. And then we have taken this a little bit more lower level view of it, where we said that we have encoder part and decoder part, which correspond to the left and the right branch in this visualization.
Okay.
So architecture composed of two parts. Now, each one of these parts itself is a stack of blocks. And then each block consists of self-attention with the feed-forward layers. So we've taken the highest level view of the architecture, and we are just breaking it down into simpler components, into deeper details. But all of this, everything we are talking about is a transformer architecture. Okay, so it's not like self-attention is something else, and then it's like part of the transformer architecture. Okay, we need to move forward. We are already 15 minutes in. We need to go forward with the course materials. We're really behind. So again, focus on this visualization, transformer architecture, and start to look at it from here, inputs, and then we are going up, and then we are going to go start to decode like we did with RNNs and LSTMs, and this is where our decoder part hits it. So we go from input all the way up to the end of the encoder, and then back to the outputs, and again, vertically up to generation. So the first thing we have done, first we did embed our inputs, and we have created positional encoding here, right? And once we have done that, we have created our input, which we called X last time. It was a matrix of the shape sequence length, input sequence length, times some dimensionality, which we call D1. Then we have passed that input, that matrix, into multi-headed self-attention, which we won't now repeat everything. We have a little overview here. Importantly, the output of multi-headed self-attention is a vector for each token. And that vector is of the same size as what we started with, but now it is contextualized. Okay, and now we are moving to what we haven't talked about so far. So after we have done multi-headed attention, there will be something called add a norm. I will come to that. But let's talk about the next bit, which is feed-forward neural network. So now we are going to take those contextualized representation and for every token and non-linearly transform them. And we are going to use a pretty simple transformation here. So, right, so just to go over this one more time. So our input is going to be of the shape L, where L is the sequence length times something like D1. We are going to pass it through multi-headed self-attention. We are going to produce some Z, which is going to be element of, again, L times D1. There's going to be something in between, forget about it for now. And then we are going to non-linearly transform it with our feed-forward neural network or multi-layer perceptron. And what we are going to use is very simple. We are going to first non-linearly transform our Z, which is going to mean we are going to use some activation and apply it to the linear transformation. So first, linear transformation means product of some weight matrix, let's call it W1, with Z, some biases if you are not folding them in. Usually we have used ReLU in the course, and it's okay, but more often you will see something like GLU, which is very alike ReLU, except that where ReLU is 0 for negative values, GLU is going to be slightly negative. So this helps with not having gradient being exactly 0 there, which we know can result in not learning because we can get in the settle point. So this is the non-linear transformation of our Z. And here we are going to do just another linear transformation. So W2 plus some bias if you care for them. The reason why this is simple, just having a nonlinear and linear transformation is because it works well enough in practice. So empirically, people have seen that adding more depth here doesn't really help. Simplicity is great if we can have, right? Like less parameters we have here, and if you can still learn with them, that's great. So this is simple enough and works, okay? One important thing here is going to be that here, you are typically going to do what we call up projection, which means that you are going to transform this vector, each one of these vectors in this matrix Z, into vectors that are of much larger size. So typically, W1 its shape is gonna be, let's call it DFF times L, the way it's written here. This DFF is typically going to be 4 times larger than our D1. And the idea here is that you want to, it's going to be very hand-wavy what I am going to say now, but this is because this is what intuitively we are trying to achieve by producing a larger vector out of a smaller one. The idea is that now the model gets to learn a bunch of useful features here, much more than we have in D1. So if D1 was 1,000, you give it a chance to learn 4,000 features, 4 times more. However, then with W2, we are going to do down projection, and we are going to return this vector, which is now 4 times larger, into something that's of the original size. And the way you can think about it, now we're almost like making a summary of everything that was found to be important in these 4,000 dimensions, again into 1,000 dimensions if D1 was 1,000. Okay, so there is going to always be some up projection and down projection in any modern LLM. But the layer itself, feed-forward layers here are very simple. Yeah.
Do we use GLU over leaky rel just because of the continuous?
I don't actually know, honestly, like what was the reason behind choosing one of these real versions over the other. If I can make a guess, I would say that obviously when ReLU was introduced, people understand that setting the negative values to exactly 0 is a little bit harsh, right? Because you may get a lot of zero gradients with 0 gradients. Basically, any version of gradient descent will be stuck. So I think it's if a bunch of researchers have read this paper, they will probably be like, oh, we need to fix this bit, and they have different ideas of how to fix that. And all these papers came together at the same time, so it can be what kind of sticks can be who has a better code base. Okay, transformers was introduced by people who weren't at the Google Beat and Google Brain at the time. Maybe, you know, they had stronger connections with the authors of GLU and so on. Or it can be like empirically one works slightly better than the other. But I don't know exactly why. I wouldn't think there is anything super foundationally important there. Yeah. Yes, please.
Are these weights here gonna be like the weights for our multi-ed attention where we do some sort of pre-training beforehand to get some good values for them?
Yeah, so every time I mentioned Wayne matrix so far, in 2017, that was randomly initialized matrix, which was then trained from scratch. Then we are going to learn about pre-training, and those will never be random, rather pre-trained. Okay, unless you are pre-training the model from scratch, which people still do to this day, right? For pre-training a model, right? Okay, so this part super simple. This is where things get a little bit poetic, and I'm not sure this is, you know, I think that having some intuition is great, but you should also be too careful that you don't make a huge ordeal out of it. So what's written on the slide that I am using from someone else is that where in self-attention, every token embedding was looking around to self-attention mechanism to kind of get what's important for processing its own embedding. Here, you can think with like that each token embedding is now for itself thinking what is important to keep from the, you know, what it has learned so far, because there is no token to token operation here. It is just on a single token, we are transforming it linearly and non-linearly. Empirically, this is where researchers have shown that lots of the world knowledge is encoded in these layers, so in these matrices. For example, if you want to know if you're prompting a model with the current president of US is, and it correctly answers this question, you might be wondering where in its parametric knowledge that's encoded. And researchers using some techniques we won't talk about have found that these are the layers that often store these facts. So then something called unlearning had emerged, where you are trying to unlearn a fact, and you would typically target these parameters. Okay, so now we are going to get into just a few more details to finish the encoder part. So here we are going to also introduce something called the residual connection, which is a super simple thing. Whatever is the output of the previous module, be it a multi-headed self-attention or the output of our feed-forward layers, you're going to add the input embedding together with the current representation of that token. Any idea why we would do that? What would be the issue that this could address? I'll give you a little hint. Imagine what is happening with self-attention. What I said?
Yes, so as you're multiplying the every attribute by each other, it's their flow values, number getting smaller and smaller.
Okay, number gets smaller, but where are we actually multiplying matrices? You mean like just through these transformations?
Yeah.
I think here you still, you don't dictate what the values here are going to be. So these aren't necessarily super small, right? So I wouldn't say that's necessarily an issue, although that's a good thing to have in mind. I would rather you to think about something that's self-attention, what calls. It's kind of a feature of self-attention, but it can kind of, there is an expression for this, I forget. Yeah.
Because somewhere maybe what can happen is that the token will attend to a bunch of other tokens, but then kind of forget about itself in a way.
Perfect, yeah. Yeah, exactly, right? So our feature of self-attention is to produce contextualized representation, but now as we, stack these self-attention layers, we are contextualizing. Maybe at some point we literally forget where we started, right? So in this way, we can, by adding the token embedding, summing it in this residual connection, we always remind the model, right, you learn something about how this token can be understood in the context of this larger piece of text, but don't forget in base form what this token could be. So that's the idea. Super simple. So whatever is the output, current representation of the token, you add its original token embedding together with that representation. Now layer norm is introduced, and maybe for kind of you mentioned that the values might get too small. I'm not sure that they do get small. Rather, what it's observed is you kind of want to skip the numbers in these representations to be roughly between 0 and 1, because that's good for the stability of the train. And what can happen is that you have a few outliers. And now because you have these outliers, the gradients might be larger for these numbers. And then what happens is that you make a massive gradient descent step for those outliers. And you kind of want to avoid that. You don't want to make some examples be more special than they are just because in their representations we ended up with higher values. So what we do is layer normalization. You basically take the output of whatever module you want to normalize, and then you put its values in that vector between 0 and 1, but not with the softmax. I'll immediately say that we won't use a softmax here because we want the mean of this vector to be 0 and standard deviation around 1. And there are going to be two versions of this, and I will introduce them in a second. Let me first introduce how we do layer normalization. So you have a current token representation. Remember, and I think this might also be confusing, here we have a matrix, which is a representation of all token representations, right? Each row is a token representation here of the first token, here of the second token, and so on. With layer normalization, you're going to apply it row-wise, as you did softmax in self-attention. And what it's going to do is going to calculate the mean and the variance of values in that vector. And then it's going to basically normalize it, this vector, such that its values are in a collectively have a zero mean and standard deviation of roughly 1. Now, there are two extra symbols here, gamma and beta, right? And these are actually learnable parameters. So not hyperparameters, not something we fix manually, rather initially random values, with pre-training they won't be random. And these values basically gives us a little bit of flexibility of determining what is the exactly mean we are going to normalize to. So if we didn't have them, we would normalize to exactly 0. Maybe we want a little bit of flexibility, right? Like not necessarily exactly 0, but somewhere around. And this is what gamma will help you with. Whereas beta will help you with, okay, maybe variance should be around 1, but I don't care if it's slightly more or less. Okay. And now in the original transformer, layer normalization was done in this sequence. So you have your input, you produce your input to your, let's say, encoder block, you have your self-attention, then you do the residual connection where you add input token embedding together with the contextualized version. Then you do the layer normalization, then you do feed-forward layers, and then you repeat residual connection with layer normalization. Soon after, people have noticed that actually, and I don't remember whether there was some kind of principal theory behind this or they just played around and found better results. But what they found that if you do input to the module or block, then you do normalization, then you do self-attention, then residual connection, then normalization, feed-forward layers, that's going to work better. So all modern LLMs have this what's called pre-layer normalization. So if you heard post and pre-layer normalization, remember that original Transformer 2017 had post-layer normalization after people introduced pre-layer normalization, and that's the one we use to this day. Also, people have noticed that there is a layer normalization I have introduced in 2 slides ago, where you basically are normalizing vectors for its values to have 0 mean and standard deviation of roughly 1. These days in modern LLMs, people are typically going to use RMS norm, which is just a slightly simpler normalization, which turns out works equally well in practice. So here, basically, you take values in the vector and you divide them by the square root of the average of the squares of the values in the vector. And you still have that gamma to kind of tell you, all right, gives you a little bit of flexibility, but we don't need beta anymore. And that's great because then you have one learnable parameter less here. Okay, so with all of that, we basically now understand the encoder block. And let me just go one more time over this. We start with text, which is tokenized, and we have L tokens in the input. We have a token embedding for each one of those in our embedding matrix, which is now randomly initialized. And we make embedding lookup, we take token embeddings of those tokens, we produce an input X where each token embedding is stacked row-wise, one over the other, in the order that tokens appear in input X. Great, that's our input. And now we are going to place this in a first encoder block, and then we are going to repeat this encoder block. So first, encoder block takes this input. It produces for each token a contextualized version with multi-headed self-attention. Then we do the residual connection and layer normalization. in the original transformer. Then we take the output of that module, which is again, for every token, we have a representation. We are always having that, a sequence of token representations. We make a feed-forward neural network transformation, which is just a nonlinear plus linear transformation of each token embedding. And then we again add the residual connection and do the normalization. And what we end up with, and this is important that you understand, is token embedding, some representation for every token. So we started with a matrix of a shape L by D1. We still have L by D1 matrix after each point, right? And this is an important bit that I think might have been the confusion at the beginning of the class. So we have done all of this once, and that's one encoder block. Now the output of that encoder block is a token representation for every token in the, which is again L by D1 matrix. So now we just repeat these operations. And what's important to say, which I kind of assume that it clicked for you, but maybe it didn't, each encoder block will have different weight matrices, right? So we will have again some weight matrices W1 and W2, but this is going to be for encoder block, let's say E1. Okay, when we come to the next encoder block, you can change the superscript and then kind of hints that you have different weights. So every encoder block has a different weights, but everything else is the same. And we do what we always do in deep learning, output of the previous layer. Now a block, a sequence of layers is input to the next block, right? This is how we are stacking them. Yes, please.
So you're saying that the blocks are, it's the outer rectangle in this diagram.
Yeah, that's right. So everything here, like this, you see this box where we have n by here, that's one encoder block.
Oh, and by, yes.
Yeah, so basically it says repeat this block n times.
Okay,
Yeah, and this whole thing with multi-headed attention, residual layer norm, feed-forward residual and layer norm is one encoder block.
and then the input is the same at each block.
No, that's a crucial thing to remember. So the output of the first block is going to be input to the second block. The output of the second block will be input to the third block. Basically the same concept of deep learning we had previously, which was simpler. We had like layers stack. Here we have blocks of layers stack, but it's always the same principle of whatever is the output of the previous layer is input to the next one. They're vertically stacked. Maybe that would help if we can.
Okay, the textbook just had one illustration where it showed them horizontally stacked, but maybe it's using a different sense of the word block. It's using them vertical stack for each input token, which it makes sense if the input is just a stacked, is a matrix of the stacked token embeddings, then you'd only stack it for.
Yeah. I think the only part where we have horizontal visualization was when we had the multi-headed self-attention. And that's where you had for a single token, you had these multiple vectors that we have concatenated in a big row. And then we downsized it to another smaller vector. So maybe that's where this confusion comes from, but that's that's not a block, that's just multi-headed self-attention. Yeah. Okay, so as always, encoder serves to encode the input. Now comes the decoder part, as we had it with our RNNs or LSTMs. Okay, so now we haven't produced any output, and this is what comes next. Now, remember when we were talking about translation, we said we encode the source sequence, and now we want to generate the target sequence. Try to be in the mindset of thinking about machine translation, because it's a great example for encoder-decoder architecture. So if I had sentence in English, let's say, I have just produced a very involved representation of that source English text. I have a sequence of very contextualized, very nonlinear embeddings for each token in the source. And now I want to start generating our the output sequence or target sequence. So you can again imagine that you start with some beginning of sequence token, and you want to start generating the next token, which would be the first token in the translation. Okay, so we have encoded, we have produced this sequence of highly contextualized vectors. So now I've placed BOS in my output. Now we are talking what we are going to do after having BOS in the output to produce the next token. That's the next thing we are going to talk about. Okay, so this is basically repeating what you guys know very well, which is basically the idea of language modeling to produce what is the next token. You need to calculate the probability for every token in the vocabulary, conditioned on what you have seen previously, which is your source sequence. So to do that, we are going to basically repeat everything we have done in encoder with few little changes. Okay, so again, here my outputs right now is just the beginning of sequence token. I will do the embedding lookup in my embedding matrix. I will get the token embedded for the BOS token. And I will, if I use positional encoding of a like positional embedding, I'm going to add the positional embedding for position 0 to the token embedding. If I'm using rope, I'm going to just rotate things in the attention matrices, attention mechanism. Okay, so now we basically again want to have this notion of, I want to attend to tokens I have generated so far. So imagine we have generated beginning of sequence, and then this is and now I want to generate the next token. When I'm processing A, I want to have a mechanism, a like self-attention, that allows me to look into what are the previously generated tokens. So this maybe seems not counterintuitive, but whatever when we don't have a long text. But imagine I am generating a book, since like every Amazon book these days is generated, right? So there is an idea that we can generate very long sequences here. So when you come at the position 1000, you still want to be looking where, you know, like have a mechanism to remember what you have generated in the first place. So that's great. One issue here is that in our self-attention, we could look into future tokens, right? That was possible. And you can say, well, it doesn't matter. I'm just going to have this many token in the input anyway. So this will never happen. And you're true. At the inference time, this would never happen. But remember when we talked about teacher forcing, when we said, well, to speed up training mostly these days, we want to construct the input we actually want to generate for a given source sequence. And regardless of what our model thinks the next token should be, we are going to place in the input what has actually been observed in the data. Okay. So if we do that, great, that's going to speed up training. However, now here we would have something that have appeared in our data, such as grade. And no, we cannot allow the model to look into those future tokens, right? Because that would be mega cheap, right? The model would then learn to memorize the data and would have no generalization capabilities, right? So we need to we want to do two things at the same time. We want to have a fast training by teacher forcing, putting the observed data sequence in the output tokens, but we want to do it, that would mean that here we need to fix these attention mechanisms such that we don't look into future position, and we need to do it in a way which, again, won't introduce any for loops or anything that's slow. Okay, so the way we are going to do that is by calculating the attention matrix the way we have done it previously in the encoder block. That means that we are going to get a matrix of the size L by L, where in every row, for example, here for dessert, we are going to have importances of every other token in the input for processing dessert, right? So these values are between 0 and 1, and they sum to 1. This one says how important token E is for processing token dessert. And we want to make this upper triangle in this matrix such that here are zeros, right? Because during the training, we should not know how important next token is to life if we have not generated next token. We should not know how important is short to is if we haven't generated in theory that token, right? So everything in this shaded part of this attention matrix should be 0. Okay, I hope that's clear. One thing, imagine I have zeros here. What don't you like about these numbers here? Yes, please.
You know, some to one.
Yeah, exactly. I lost my nice distribution, right? Like this is not summing to 1 anymore. Okay, so what could we do? Softmax, just renormalize, right? So here I can settle these values to 0, and I can apply softmax again to normalize these values, right? And that's gonna be okay. This is just like attempt to see whether you can see other way. That's a little bit nicer and avoids applying softmax twice. So imagine I didn't set these to zeros, but to something else. What other value will then do things at the same time? Yeah.
You want to do negative infinity?
Negative infinity, right? So if I had set the values here to negative infinity, applied softmax, then this will automatically be set to 0. So these are basically 2 ways to do the, what is now called mask or causal attention. These are not random terms. This is something people will use often. So try to remember mask or causal attention. One way is you first get attention scores unnormalized. Do we remember which product of matrices gives us a normalized attention scores? Yeah,
It's the query just.
yes, exactly. Query transpose times a key matrix. So we get attention, some numbers there which are not normalized, right? They resemble dot products, so between 0 and 1. You can then normalize them through softmax. Then you can set the upper triangle to be 0, and then you can normalize again with another softmax. Or you can get your unnormalized values from the, again, query transpose times key matrices. And then you set the upper triangle to be minus infinity, negative infinity, and only then you apply softmax. And I think it's a no-brainer to use this one, right? Okay, so this is something you're going to implement in the assignment. So this is very, very, very important to do properly. Okay, now we have produced for every output token a new representation with the mask attention, which attends to previous tokens in the output sequence and doesn't look at the future, utilizes the teacher forcing. One final type of attention we are going to introduce is going to be so-called cross attention. Basically, we are going to have these representations of the tokens that appear in the decoding step, so output tokens, and we want to tweak them relative to our encoder representations, so representations of the source sequence. So here, you're going to use, again, self-attention in a particular way. Your keys, queries here are going to be the representations that come from the decoder, right? So you see decoder here. Your keys are going to be representations that have been outputted by encoder. And the values are going to be, it says encoder here, but let me think about this. I wouldn't write this in this way because we are changing the decoder values. So I think there is a mistake actually here. I will double check after the lecture, but this isn't intuitive to me. So I'm going to use this visualization here. So here, this is the matrix that corresponds to all the output tokens. So imagine you have n tokens so far, and they are all of the some dimension d. So we have placed them row-wise. You are going to use new outputs to serve as your keys and your values. However, your encoder representations, which are representations of the source sequence, they are going to serve as query. So again, by doing the multiplication between queries and keys, you are measuring how much tokens in the source sequence are important for the tokens in the decoder sequence or the output sequence. Knowing that information, you are adjusting the values, which are the representations of the output tokens. And you adjust them by how much information in the input sequence is important. So yeah, I acknowledge that there is a mismatch between what's visualized here and what's written here. So I will double check what is correct. But to me, this visualization makes more sense. Yeah.
Regarding the inputs from the encoder versus the decoder, I mean, obviously the decoder is going to be from whatever decoder block we're working on, right? But the encoder is a bunch of encoder blocks stacked on top of each other. So when it comes to taking in the inputs, are we just considering the final encoder outputs, or are we considering from a specific encoder block?
Yes. So, okay, the question is, which encoder block gives us outputs that we are going to use for this cross-attention, right? So here, that's an actually great question. I'm not 100% sure because you could take the final encoder blocks representation at every decoder block. So it doesn't need to be that you need to take first encoder block for the first decoder block, right? Because they have already been produced.
Right.
So I would say the final ones, but let me also double check that detail. I'm pretty sure it's the final one because that's where all the information that we need is stored.
That would make sense to me.
Yeah, intuitively, that's kind of what would make, what I would do, but I will also double check this detail.
Okay.
Yeah.
I'm a little bit confused where the inputs from the decoder are coming from. Is that the goal label translation or that some other?
Yeah, so the question is where are the inputs to the decoder? So it's a delicate nuance answer, right? At the inference side, so when we are done with training, all you can do is generate one token at a time, right? So when you start with your EOS token, which says in generating, you generate this token and then it becomes input to the next token position and so on, right? So you are applying the full stack of decoder blocks sequentially. You repeat them as many times as there are generation steps. During training time, we would like to use that feature forcing we have learned previously in the course, where we take the goal sequence, target sequence, such as goal translation, and we place it as an input to the decoder. And instead of doing this stack of decoder blocks sequentially, we do everything in parallel, right? And regardless of what our transformer decoder thinks the next token should be, we pretend the next token is the one that we're in. And then we talked previously about like benefits and downsides of that. With a model of this size, you're definitely gonna do feature force integration. All right, so we are going to have the feed forward and residual and layer norm the same way we have used them in the encoder block. And again, as we did with the encoder block, we are going to have multiple decoder blocks. Again, the output of the previous decoder block is the input to the next decoder block, and so on, all the way to the output. So now, the goal was to actually generate something. So what is coming next after I have generated a representation for the last token in the targets, whatever. I have generated something so far. I have the last token among my generations. I have a representation of that token coming from my set of decoder blocks. What is going to come next if I want to generate the next token?
Nonlinear activation function, and then your final outputs, like a softmax. or something.
Okay, you're telling me layers, but to answer my question, tell me like what are these layers achieving?
Aren't they generating like a probability distribution of
Yeah.
the next outputs?
Yeah, exactly. So by having, so we have a representation of the last token in the target, in the output sequence so far. And we want to produce the distribution over the vocabulary such that we can sample from that distribution using something like nucleus sampling, right? To come to that distribution, we do as we have, we repeat the sequence of layers we have used in this course many, many times, which means produce logits out of that vector, which means linear transformation into a vector of the size of the vocabulary. I get unnormalized values there, which I don't like because as we know that don't tell me what is relative importances are hard to understand. So we apply softmax to that vector, and this gives me a notion of distribution over the vocab, and then I can do nucleus sampling out of it. Okay. So that's it. It's been like a couple of hours, but we managed to go through the entire transformer. I know it's a lot, right? And it's quite involved and much different from, previous neural networks we have learned. So if you feel like you don't get everything quite yet, that's expected, right? Because it's personally took like few times going over this architecture for everything to really be clear to me. Despite it being a little bit intricate, it's really important. As we said, it's a core architecture for many modern LLMs. It's important for you to know it. You are going to then implement a slightly simpler version of the your assignments. So you will have a chance to kind of go through what we have learned in these lectures through implementation. And then things should be much, much clearer. And there you will be able to use PyTorch functions to create like linear layer, right? You won't need to write everything from scratch if you don't want to. Yeah, so just remember that from encoder part, I produced these sequences of highly contextualized embeddings for each token in the input, and the decoder part as always is responsible for generation. So given a first token to generate, we are going to do operations to generate next token. All right, let's take a little break here, and then we are going to talk some more about transformer and the tasks.
I think it makes sense to you, so it's how it looks. It's right here. It's just separated, so. And then, so here, we just treat it as a wizard of, multi-dimensional. Okay, so.
Yeah.
Here, basically, each one of each, you know,
Is what's,
okay, so,
Yeah.
yeah, so basically, the transformer that I have shown you, that is a step before the blocks, and you apply it for every token, right? So you vertically apply blocks per blocks. However, you use the same blocks for the next token as well, right? So when I say there is a vertical line, you can imagine you apply them for each token, but the weights here are shared, right? So weights of each block, you're going to apply to the first block and the next token, right? So they are not, it's not like the second token has weights that are specialized just for the second token, okay? So basically, you can almost imagine stacking this whole transformer over tokens. Implementation wise, we don't do it like that because we like everything to be centralized for faster training.
okay, so how this, yes, so it's the same. Price for each.
Yeah.
For each token.
Yeah, so actually, if you don't mind, can you move there? See how I have written this X to be matrix, so the shape L by D1. So that's all these input tokens, I think their representation as I stack them otherwise. And then I have, the way I have explained, transformer architecture, everything is standardized, right? So it's just like this vertical.
Using an open matrix.
Yeah.
For instance, if we're in this case in this diagram, we would have like a bunch of tensors, just one-dimensional
Yeah,
tensors for each token.
Yeah, so basically this visualization is, if you, instead of having L by D1, you are having just one row. Then you are applying everything to that single row. You get the output for that single row. And then you move to the next row and then you apply it to the next row and so on. So it's easier to write everything as matrices, so you don't need to have this full line, which we don't like, so it makes everything slow.
Did you guys get?
Yes, oh no, for loops, yes.
Yeah.
And in this case, you'd have to do the attention over all the separate vectors. But in this case, we can do attention, which I think was really helpful, because you have the slides of on the attention lecture. Like the last couple slides, I don't think we covered them, but it explains the key value really clearly.
Okay.
If that's helpful, I don't know if that's helpful to you, but help me understand how
Yeah.
we're using that query to attend over all the keys.
Yeah.
Which key the query matches up to.
Yeah. Yeah, that's right, yeah.
Okay, great. Okay, that helps me understand better.
Yeah, so
Okay,
I
and
think
then,
there is slight difference between like visualization, how you want to implement this. Something as visualization, because it would be starting from an L by D1 matrix, rather also have D1 vector.
if we were to.
Yeah. Then, basically notice how W1, W2, they are all against same matrices. They are multiplied by a vector, this Z, which is now a vector matrix, which makes me think there was a mistake here. Okay, I need to say this was a mistake. It's not by L by D1. I will say this. So your weight matrices will never have input dimension as a part of shape. These weight matrices will always be one dimension to another dimension, but never the implicit effect. So I made a mistake here. Yeah, yeah.
Okay, so for each block, so we get more information about the different tokens.
Yeah.
We keep the same weights, but it's by having stacked blocks and using attention, this is how we get information between tokens.
Yeah, yeah.
That's-
Yeah, yeah.
Okay, and then I still have a question. How is it different when we're, how do we calculate the input embeddings?
Input embeddings are initially,
It's like-
yeah. Okay, yeah, I will answer that question later. It's just, you have embedding matrix and you do the load in the embedding matrix. Yeah.
And we have to calculate the embedding matrix using an attention, same process based on attention.
No, input embeddings are always gonna be just embedding matrix.
The static embeddings.
Yeah, that sounds,
Okay, maybe let me correct myself. In a higher encoder box, they're going to take the output of a previous box, and it's gonna be into the next one. I think very, very quickly, you're going to start with those embeddings, by looking up the embeddings.
It's like word to it.
Number to it. For to it, it's not gonna be randomly applied to the metrics, which we're gonna learn.
Oh, it starts with random initialized. Which we.
Okay, let me cover.
I'm actually reading more on that.
Yeah.
There's an information from my own element is already. What I've already done was like it's a space. Like L, E, and he just replaces it with LE.
If you're talking about random initialization of weights, I don't really know how something specific.
It shouldn't merge it, right? The space should still remain.
Stuff like behavior initialization.
To put family or cheese.
Yeah, I know that
You
reasons where
before we
do pre-training.
Do you like conversation?
I think it's called like.
The word visualization cheese.
Was the weights.
Yeah, but talking is when you're in the,
Non-zero.
so if you're just working at LE and AR.
Yeah, so non-zero.
Over here is this word.
And that's what we did
It should
before.
just be LE space, or D.
Yeah, for. Yes,
So.
do that for your points.
Are.
Technically, there's also a bias in it.
Have G with the dot, so small, we know that we can merge. Yeah, but I think without.
That's what I did.
Before the whole margin looks like it's great, but it's not great.
That's it.
Yeah.
Yes, that was an option.
But there's no other marriage that creates LE.
Looks like we're gonna be moving pre-training.
And then you can't have, because you're
Yeah,
looking
those
for
forces
space.
that thing.
I see.
So like imagine there is like a G.
I think he said this bad, we still use. For the embeddings.
The result.
Or at some point we have.
So
We learn the embeddings.
The embedding, so you had use pre-training fun. Initialize for
So constantly, around it would be the, if I'm making mistakes. But I just feel like right now,
When those pre-trained
I
bonds.
wonder why,
That's
whatever,
really.
this might become a question of why doesn't merge. You're trying to
It's kind of like
understand,
how.
but I feel like this unit test won't help us debug that.
Someone had
because-
trained love first.
Yeah. I think it's kind of so if nobody could try, it'd be great to find just an email and doesn't work.
I think it's.
Okay, let me clarify one thing that might still be a little bit confusing. So, first of all, before the first encoder block, we have an embedding matrix, right? So that's you can call it the layer 1 or layer 0, whatever you like. So that's gonna be a matrix of, as always in this course, size of your vocab times dimensionality, which we call D1, right? And when I give you some input text, that text is tokenized, right? What you're doing is the lookup operation. So if I will use numbers here, 5, 0, 1, and so on. Basically, what I do is looking for rows with those indices. So here I have 0, 1, 3, 2, 3, 5. So I'm going to retrieve this row, 0 row, and 1. And I'm going to stack them in the order they have appeared in. So this one is going to be first, then this one, and then 1, right? So they're gonna look like this. Imagine actually that's the entirety of my input for simplicity. So now the shape of this, which we have called X, is L times D1, where L is 3. Okay, so now imagine I'm trying to think of notation that will be helpful for this. So we have encoder block, and input to encoder block will be outputs of the previous output of the previous of encoder block I-1, right? So when we have our first block, what we have is this X token embeddings, right? So when we have encoder block E1, E0 is going to be X, right? However, when we have encoder block 2, its input is the output of E1. Okay, so only first encoder block is special, it has a special input. All the other encoder blocks take the outputs of the previous block as their inputs, okay?
Yeah.
And now one crucial thing to not be mixing up. So nowhere when starting to talk about transformers have I mentioned word-to-vec, right? So this embedding matrix initially is random. And this is where we do our lookup of token embeddings. It is going to be part of our weights parameters that we are training with the entire rest of the transformer architecture. So it's not word-to-vec. Don't mix word-to-vec for here. This is just a normal random embedding matrix, okay? And we are going to come to it when we talk about how we pre-train these models. Another thing I have to do is correct myself. Unless I removed. No, I didn't. So here I made a mistake. I said W1 is of this shape. This was wrong. And one way you can always check whether I'm wrong with shapes of weights is if I introduce the input sequence length in as a part of the shape of a weight matrix. Weight matrix is input invariant. So here, when I was explaining someone, I realized, oh no, my weights have L, which they should never have. And here, instead of L, we should have D1. The reason why I made this mistake is because my Z, its leading shape, leading dimension is L. So to make a matrix product work, I had to have L here. And the reason why this is all mixed up is because I and the author of those slides were making these products in a different way. So here, this is now correct. And instead of, yeah. Okay, so weights they must be input invariant. Otherwise, we can't reuse them for differently shaped inputs. Okay, so how do we have only 5 minutes left? Is beyond me. I feel like time is moving with a different pace this year. Okay, so I'm going to finish with showing you different kinds of transformer variants that have emerged since the original encoder-decoder transformer has been introduced. So in 2017, Attention Is All You Need was introducing transformer that was encoder-decoder. And then researchers played around with the different versions. And actually, modern LLMs are mostly decoder-only transformers. So that whole encoder block we have learned, we just don't have it. And what you do is with your source sequence, well, you can still represent it with decoder blocks, right? Like you have you place it into the decoder blocks, and again, you simply don't care what the decoder thinks the next token, right? So if you have L source tokens, you just pass them through your decoder. And then when you come to the last token of your source sequence, you can start generating the next token. And again, your decoder has ability to allow that every token can look around, right, with the masked attention. It just can't look into the future, and you still have feed-forward layers and so on. Another thing that people have ditched in the meantime, then with switching to decoder-only models, is you don't have cross attention, because if you don't have encoder blocks, there is nothing to cross attend to. Okay, so that's the one that is very, very commonly seen today. However, in 2018, right after transformer architecture was released, we have for substantial time used encoder-only transformers, and we still use them for specific purposes. Okay, so it's not like one or the other. Encoder-based models still have, usage, particularly if you need a vector representation of some sequence, you will typically go to encoder-only transformers that are pre-trained. We'll learn the pre-training next time. Yeah, you would still use them to this date. For any kind of generation, you're going to use the state-of-the-art encoder model these days, although encoder-decoder is kind of potentially having a comeback. Okay, so, and then finally, encoder-decoder is the one we have seen, and it was used in 2020 with the T5 model quite substantially, but then there was a shift in decoder-only models. And we are going to go into how to pre-train a decoder-only model and how to pre-train encoder-only models, how to use them after they are pre-trained next time. So don't worry, this isn't anything, everything I want to say about this. But I want to show you this visualization of these three different kinds of transformers. So in the leftmost branch, you see these encoder-only models that have emerged right after, you see 2017 is when transformer was introduced. And then people have taken encoder-only version of transformer and started to pre-train it in ways we are going to see. And what you can notice here is that this branch has kind of stopped around 2020. And then we started to see more of these encoder-decoder pre-trained models. But then very suddenly, this decoder-only and pre-training with language modeling that you all know very well now has been the winning combination, the one that has scaled pretty well. So next time, we are going to talk about how can we tweak these weights in our transformer of different kind to be not random weights, but rather some weights that capture a lot of linguistic phenomena through training with some objective that doesn't require human labeling of that data, but it helps to learn useful features of language. One of them, as we know, is going to be language modeling. The other one is going to be something called masked language modeling. And then we're going to see, unlike with our decoder-only models, where we are going to reuse the output layer, which produces the vocabulary distribution, because we are going to cast everything as a sequence-to-sequence task, so we can reuse that output layer. With encoder-only model, we are going to have something called classification head. Basically, we are going to ditch the output layer we use for pre-training and introduce new parameters, which will require additional training for every task we want to use these models for. So yeah, next time we're going to talk about that, and then we're going to see how we can apply these things to a bunch of applications and evaluate them. Okay, I will send an announcement for Wednesday. You can expect the grads come to Matt, Bill and undergrads come here, pretty standard as always. Good luck with the assignment.